video on digital electronics. In this video, we'll be seeing what are Boolean algebra theorems and we'll try to solve some of the numericals based on it. So I have put here two images for the Boolean algebra theorems. I request you to note these theorems down. So what are theorems? These are ground truth and they never change. So using these ground truth, we'll try to reduce our equations. Any circuit is a function and hence we write an equation for it. If the equation is larger, the circuit becomes complex and hence we try to reduce it because we want a compact circuit, a compact component, a compact instrument in all. So following is a theorem, a plus 0 is equal to a. So this remains true for any of the variables. The name of the variable may change. X plus 0 is equal to x again. X into 1 is going to be x and so on. So these are some of the theorems. Theorems that you should consider most is those theorems which reduce to a single form of a variable. For example, a plus ab is equal to a. So had we implemented this using gates, we would require one AND gate and an OR gate. But otherwise, this is as good as a single variable a. So keep concentrating on such theorems which help you reduce the equation to a larger extent. Something that reduces to 1 or something that reduces to 0 also help you reduce the equation. This is another set of the same theorems. In all, we have 22 theorems. Again, we have a into a plus b is equal to a. Had we again implemented this using our basic logic gates, we require one OR gate and one AND gate. Same goes here. We require in this equation two AND gates and one OR gate, but it is as good as a. Please remember the name of the variables may change. You just have to re-implement the equations accordingly. So let me give you an example. Say I have an equation f is equal to x bar y z plus x bar y z bar plus xz. Anytime you get an equation, try to see what are the common terms that you can fetch out. So in these two terms, I have x bar y and then I can write z plus z bar plus xz. So what is z plus z bar? According to the theorems, if I see here, a plus a bar is equal to 1. So this helps you reduce the equation. Z plus z bar is also 1. X bar y into 1 plus xz, which is nothing but x bar y plus xz. So let's try to implement a circuit. If I implement a circuit using this equation, then I require a lot number of gates. So say I have x. This is an ideal way of doing it, putting a NOT gate because we require an x bar also. So we first make all the wired connections and then you can fetch whatever wires you require. So this is y. We do not require a y bar. So I'm not putting a NOT gate. Then we have z and a z bar. You can put y bar, there is no harm in it. So first term has x bar. I'm sorry. The first term has got x bar. Then you have y and z. All three multiplied means into a AND gate. Then you have x bar again, y and z bar this time in an AND gate. And finally we have x, z in an AND gate. And all the three terms are OR together, which means they are added together. So I have an OR gate here. So this is your function f. Since we have written f, I'll write it f again. If I implement the same function with a reduced form of an equation, let's see how many gates are required now. I have x. I need an x bar. I have y and I have z. So the first equation, the first term of the equation is x bar into y. Then we have x into z. And finally we OR the two. And that's your function f. So the equation here which we implemented using 1, 2, 3, 4, 5 and 6 number of gates. Same equation performing the same function is now implemented using only 1, 2, 3 and 4 number of gates. So since we reduce 2 gates, our hardware reduces and eventually our circuit also reduces. I'll stop here. Thank you for watching.